Hello humans, monophasic, biphasic and polyphasic sleepers, insomniacs and cave dwellers, and welcome to the Cosmic Tortoise podcast. This episode is with sleep scientist Patrick Fuller. Patrick is Associate Professor of Neurology at both Harvard Medical School and the Beth Israel Deaconess Medical Center, and is involved with numerous organizations including the Society for Neuroscience and the Sleep Research Society. This was an enlightening chat about all aspects of sleep and the related neuroscience. After defining sleep, we talk about the different brainwave states, present and potential future technological hacks for different brain states in sleep, some of the major neurotransmitters and hormones involved in sleep-wake regulation, the circadian clock and how we are affected by temperature and blue light, what monophasic, biphasic and polyphasic sleep patterns are, and what evidence is available for how we slept in the past, and discuss optimal sleep times and how to create an ideal sleeping environment. This was ironically recorded in New Zealand time from around 2 in the morning till around 3:30 in the morning, which totally messed up my sleep patterns. Regardless, I was really happy for Patrick's time, and I found the chat really informative and good fun. So here it is. Enjoy. So I thought maybe we could begin by hearing a little bit more about your background and what areas of research you're involved in.
Okay, great. Yeah, of course. So I'm a neuroscientist with an interest in how the brain regulates behavioral state, in particular the states of wake and sleep. And the regulation of both wake and sleep are, in fact, active processes, and these require the coordinated activity of distinct cell groups and pathways and transmitter systems in our brain. And when these systems aren't working appropriately, this profoundly affects our ability to function normally. So as an extreme example, if our wake-promoting circuitry is sufficiently disrupted, we end up in a coma. Or if our sleep-promoting circuitry is disrupted, we end up with insomnia. And so the experimental efforts of my lab are directed at understanding the location and identity of both wake and sleep promoting circuitry in the brain, as well as understanding how these circuits interact with one another to produce normal, healthy cycles of wake and sleep. We're also interested in how a little clock in our brain, which I imagine we'll touch upon on our discussion, controls the timing of sleep-wake cycles. So in the end, it's my hope and intent, I suppose, as a neuroscientist running a very basic science laboratory, that findings from our experimental work will inform, I guess, broadly speaking, the treatment of a wide range of wake and sleep disorders. And then perhaps beyond this, I hope our work will inform the development of better general anesthetics and treatments for a host of neuropsychiatric and neurodegenerative disorders in which sleep and wake are disrupted, and in which sleep and wake disruption may in fact contribute to the progression of the various diseases.
Fantastic.
I think that about sums it up.
Brilliant. Maybe we could start in a definition of sleep. So maybe you could give us a broad definition of sleep and its basic function in humans.
Yeah, of course. So sleep, and in particular the why of sleep, and that is its function or functions, if you will, is actually considered by many to be one of the more enduring mysteries and important questions in the neurosciences. And when you think about it, sleep is as vital as water and food. We spend a third of our lives sleeping, and all animals do it, and yet we still don't understand, or at least not fully, why we do it. So, and really, underscoring sort of the fascination with sleep, it's been the topic of writings by religious leaders and philosophers and scientists and other writers, quite literally since the beginning of recorded history. You can go back to the ancient Hindu textbooks, so 1000 BC, where they describe different states of vigilance. Aristotle himself wrote an entire treatise on sleep, which he titled, I think, On Sleep and Sleeplessness, and this was in about 350 BC. Then there was, Hippocrates, the famous ancient physician, who was the first really to emphasize the importance of sleep to health. He wrote in aphorisms that bad sleep and insomnolence, when immoderate, are bad. And really, what makes this history rather remarkable, why I bring it up, is that until the last century or so, the how and why of sleep remained, and really on every conceivable level, complete mystery. And I'm not sure we can yet provide a clear-cut answer as to why sleep is necessary for survival. I mean, although we do know it's necessary for optimal function, that is without any doubt. But as one rather prominent sleep scientist, Alan Reksheffen, remarked years ago, he said, well, if sleep doesn't serve some vital function, it's the biggest mistake evolution ever made, right? And in short, and really what he meant was that is, well, why would our brains go offline for any extended period of time, right? After all, the third of our lives we're spending in this day is a time of heightened vulnerability, not one in which we're pursuing biological imperatives like eating and drinking. And certainly from the standpoint of your genes, you're not procreating. And then on really the flip side of that, if an animal, be that a human or a mouse, could go without sleep, you think this would be highly adaptive, right? I mean, you'd have more time to find food and find mates and exploit the environment and conquer territories and learn and everything else that we do while we're awake. So I suppose my personal take is that sleep does many things, which may include synaptic remodeling, clearing out wake accumulated toxins from the brain, ensuring that memories are formed. But these processes, even collectively, are likely only a partial, if somewhat, unsatisfactory, at least from my standpoint, answer. But sorry, to go back to really the fundamental of your point of your question was, what is sleep? Well, sleep it's a behavioral state characterized by a few things: a reduction in motor activity, a decreased, or it's a time of decreased sensitivity to stimuli. You could think of the brain as being somewhat firewalled from the environment, and really a sort of a stereotypic set of postures. And what separates sleep from other states of altered, consciousness or vigilance, those states being things like coma or when one is under anesthesia, is that sleep is rapidly reversible and self-regulating. So I'll stop there.
Yeah, it's interesting that we require sleep because there are other animals that don't sleep. That's correct, such as ants.
Well, I guess it depends on how you want to define animals, but yeah, I think we have evidence for sleep in virtually every animal that's been evaluated for sleep. You may have to use slightly different characteristics, but virtually every animal, to my understanding, has a period of sort of active period and an inactive period, a period of quiescence period. So to the extent that they have the same, electrographic sleep, we can touch on that in a moment. That may or may not be the case. But even things like, zebrafish sleep, Drosophila, little fly sleep. Ants, that's a great question. I'm not sure. Maybe there's something specific about ants that I'm not aware of. But again, to my knowledge, across the phyla, every animal exhibits some form of daily pattern that exhibits, or excuse me, that mimics a sleep-wake cycle.
Okay. Interesting. So perhaps we could go, the next question we've got on here is, what are the different stages of sleep? And I guess we'll keep this in the human realm for now.
Okay, yeah, right. Okay. Well, great. Yeah, so what are the stages of sleep, or different stages of sleep? So, well, when we begin to fall asleep, we actually see really dramatic changes on the electroencephalogram, or EEG for short. And that's, just to be clear for the listeners, the EEG is just a way to measure the spontaneous electrical activity of the brain. Okay, so during wakefulness, the cortical EEG contains these high frequency, low amplitude waves, often referred to in popular science as brainwaves, right? Which reflect neural oscillations of different frequencies. And so in wakefulness, you see these frequencies at about the 14 to 30 hertz range. And these are actually thought to reflect differences in timing of processing of cognitive and motor and perceptual functions. And then during the transition from wake to sleep, which is often referred to in the literature as quiet wakefulness or quiet rest, the EEG oscillations predominate they drop in frequency to about the 8 to 13 hertz range, and we refer to these actually as alpha rhythms. And then at the true onset of sleep, which is what we refer to as non-rapid eye movement sleep or non-REM sleep, which actually comprises 3 stages. I'll go through all 3. The EEG waves become much larger in amplitude, which presumably reflects essentially increased cortical synchrony, and the actual frequency of the EEG slows. So during stage 1 sleep, I just told you there was 3 stages. So the first stage of sleep, you have conscious awareness of the external environment begins to disappear, and you have oscillations that start to predominate in the 4 to 7 hertz range. Then during stage 2 sleep, there was a complete loss of conscious awareness of the environment, and as well as the appearance of these sort of stereotypic waveform features. You'll see them referred to as sleep spindles and K complexes in the EEG. And then in the final, deepest stage of sleep, often called it's often referred to as deep sleep, but these waves, so-called delta waves, appear, and these oscillations are very very easy to recognize. They're very high in amplitude or voltage and predominate in the 1 to 4 hertz range. So again, very high amplitude, very low frequency. And in fact, they're often referred to, in addition to delta waves, as slow wave activity in the EEG. And it might be of interest to note that the power, amplitude, and incidence of slow wave activity, or these delta waves, actually forms the operational definition of sleep intensity or sleep depth. So, so that's kind of we kind of worked our way from wake all the way to the deepest stage of sleep. But then there's a fourth and final stage of sleep called rapid eye movement sleep, or REM sleep for short. Which takes its name, perhaps somewhat obviously, from the fact that our eyes move under our closed lids. They move very rapidly during this stage of sleep. In fact, it was the discovery of eye movements during sleep that led to the discovery of REM sleep. So it's worth probably taking a moment to describe REM sleep, because it's physiologically strikingly different from non-REM sleep, in that during this stage of sleep, the EEG becomes quite fast in frequency and lower in amplitude. In fact, it actually begins to mimic, in many respects, the EEG of the waking brain. And then coupled to this fast activity in the EEG, we see indications of activation of specific structures like the hippocampus in the brain, changes in breathing, heart rate. We actually lose our ability to regulate body temperature, and perhaps most, strikingly, our muscles actually become completely paralyzed. So REM sleep is typically associated with dreaming, and although we now know that dreaming is not necessarily restricted to REM sleep, and it's for this reason, among others, that we think REM sleep might play an important role in the consolidation and retention of new memories. So, so to pull it all together here, you have these non-REM sleep, and REM sleep cycles, and they continue to alternate in a cyclical fashion through the night, with each cycle lasting about 90 to 120 minutes or so an hour and a half to 2 hours. And you typically see that most of the slow wave non-REM sleep occurs in the first part of the night and occupies increasingly less and less time of each subsequent cycle, whereas REM sleep episodes, on the other hand, generally become longer through the night. So now, would you like to hear about something I find kind of fascinating about REM sleep? It's something people might be interested in hearing about.
Absolutely.
Okay, great. So there's this really rather fascinating, if terribly debilitating, disorder, or sleep, what we call sleep parasomnia, called REM sleep behavior disorder, in which muscle paralysis, as I mentioned a moment ago, where muscles are paralyzed during REM sleep, it actually fails to occur during REM sleep. And so when this happens, humans and animals may actually act out their dreams as if they have effectively lost their neurological brakes, right? And this has led to some very serious injuries. Like I said, it's not something to take lightly here, but because it's not only to the individual, but unfortunately, that is the individual with the disorder, but also to their bed partners. Some very fantastically tragic injuries. But fortunately, we can actually treat REM sleep disorder with medications. And then there's an even more fascinating link between REM sleep disorder and, in fact, several neurodegenerative disorders, in particular Parkinson's disease. And by link, I mean that at least in men who, as a gender, are disproportionately afflicted with REM sleep behavior disorder, the diagnosis of this disorder is actually hugely predictive of developing Parkinson's disease or some other diseases in the Parkinson's family. They call them synucleinopathies in the ensuing decade. But there's a silver lining to this, right? So because once you have the diagnosis of REM sleep behavior, once the diagnosis of REM sleep behavior disorder has actually been made, patients then can be monitored and treated at a far earlier stage of the other disease, be that Parkinson's or other. So thereby kind of delaying the onset of the more, I suppose, insidious and debilitating features of the disease. So
fascinating.
I'll stop there.
No, that's great. Any tangents are very welcome. Always are.
Lots of fun.
Yeah. So I'd like to rewind slightly just back to the names of the brainwaves here, just briefly. So when we're in a waking state, am I correct in assuming that it's called the beta? The waves are called beta?
Yeah, what you see a lot of in waking is beta, and you also see when there's active sort of cognitive processing going on, a fair amount of very high frequency called gamma waves. Those can start as about 60 hertz and range up into to a couple hundred hertz. So that's correct.
So we've got beta and gamma and delta and alpha. Are there any others?
So there's alpha waves, right? And those are going to be in the kind of the quiet waking period we talked about. And then delta being in the deepest sleep. And there are also some, I mentioned in stage 1, you start to see some in the 4 to 7 hertz range. And that often would be referred to, although the bandwidth's a little bit narrower than 4 to 7 hertz, it would be referred to as the theta range. So yes, you have alpha, beta, or gamma, beta, alpha, theta. There's a sigma in there too, and then the delta waves. Correct.
Because I'm curious about how much research has been done in induction into certain states of brainwaves in people. There's a lot of what seems to be woo-woo out there with things such as binaural beats and other methods of people attempting to put themselves into these different brain states. I wonder if you better elucidate a bit on that.
Yeah, sure. Okay. Well, right. So, can sleep-like brainwaves be induced, right?
Yeah, exactly.
in people, right? So the answer is, in short, yes. The most common, if I guess, proven way to do so is using a technique called transcranial magnetic stimulation, or TMS for short.
Nice.
And directly related to your question, there was actually a recent study that showed that TMS pulses could trigger these slow oscillations and enhance slow wave activity in sleep, both locally, in other words, where the coil was applied, and globally. And so the authors of this work argued that endogenous sleep rhythms could be potentiated or enhanced non-invasively and non-pharmacologically using TMS, and they actually went a little bit further to speculate that TMS could be used to enhance the if you will, a restorative value of short periods, short sleep periods, so like power naps, right? And reduce, of course, the negative symptoms associated with insomnia and aging and other neurological disorders with disturbed sleep. So, and maybe I should take a second for the uninitiated to describe the TMS a little bit more. What it actually, so it actually takes the form operationally of a non-invasive coil that is applied to the head above the targeted area of the brain. So for example, when used to treat depression, which is, I guess, arguably its most common clinical application, the coil will be placed over the prefrontal cortex, as this part of the brain is really involved with mood regulation. And the magnetic fields produced by the coil don't affect the whole brain, right? And that's because they can only basically reach a few centimeters into the brain at most. Beneath where the treatment coil is. And so in a nutshell, the TMS magnetic field moves into the brain, produces a small electrical current, and these currents activate cells within the brain, which then are thought, of course, to release their transmitters. So it's a cool technique, and it may have some pretty important clinical applications, but it's also one for, honestly, Ryan, for every study that says it works well, there's yet another study that says it's not terribly efficacious. So there's that. I think the jury is still a little out. Excuse me. And there was also, I'm sure you're aware of this, but there's also something of a growing concern that people will literally try and kind of make their own coil systems at home hack their own brains, if you will.
I know someone. I know someone that has.
Okay, yeah. And, on the one hand, more power to. On the other hand, it could possibly be to bad effect. So I would urge caution. And anyhow. So if you know someone, this is actually a real thing. So.
Yeah, absolutely. So more research is needed to have a definitive answer. But I'm curious for the people attempting to enhance things such as power naps. So are they applying these? What are they called? TMS.
Well,
are they applying them before they sleep? Are they applying them during sleep?
Yeah, it's an interesting question. I think one would have to probably apply it during the sleep process. But to the extent people are doing this in their own homes, I really would have no great sense of that. It could be done in the clinic, but again, the applications right now I think are more theoretical. Again, I think we have some data, and this is not my field, that there's this approach has been somewhat effective in treating certain types of depression. And again, as I told you a moment ago, the paper, the authors did argue and speculate this could be used to enhance, but of course, in the paper they did not present data of this. It was more of a speculation. So,
sure.
I typically wear, to no surprise, I'm sure, given what I do, my scientific hat most of the time, and then when I'm wearing that hat, I tend to also be walking the road of systematic doubt. So I like data, I like evidence, and I don't have that in hand for TMS. I think there's conceptually it's very appealing. I think there's some real potential, but I think we need a lot. For example, we would need controlled and otherwise rigorous human studies to prove that this is a technique that will or a technology that will actually achieve what people have claimed it can achieve. Otherwise, it might move closer to the category of woo woo as you described.
Sure. Yeah. Well, let me throw a couple more of these things at you just briefly, and
Sure.
And you can let me know if you're aware of any research or if you're aware that it's complete nonsense. Binaural beats.
Sure. Yeah. So okay, great. So I have to sort of acknowledge my agnosticism here, right? So I'm not really well acquainted with the research studies that have been done with binaural beats and sleep specifically, other than having read I think maybe one, and it was a questionnaire-based study. Which indicated a possible increase. I think what they said was in perceived sleep quality in folks that were using binaural beat technology. But I do have a sense of the principal concept, which is that and for your listeners, the idea is that that an auditory illusion is produced by applying sounds of slightly different frequencies to the two ears, and the thought is that you can then entrain brain waves and hence behavioral state, I suppose, by using appropriately chosen auditory parameters. So again, it does sound a bit woo-woo, doesn't it? But and it might be. But I do know that some people swear by binaural beat music as a part of their meditative practice, for example. And from that standpoint, and as a proponent of meditation and mindfulness practices, I'd say if it helps one in their meditative sessions, then yeah, why not embrace it? But will binaural beat help one achieve sleep or more restful, quiet wake? I'm unsure, but again, I don't really see the harm in trying. It's a pretty non-invasive type thing to do. So
yeah, I mean, I've tried it, and a few of my friends have tried it, and it does seem to change the state somewhat. But it was just there's a lot of claims on these. There's a lot of them on YouTube, and they're all over the place. There's a lot of claims that they're going to entrain your brain to a certain state, and so a certain theta or alpha or beta or whatever. And that's what I was I couldn't find any literature on anywhere. Well, you've mentioned meditation there, so why don't we jump into that one?
Sure.
So is sleep research concerned with meditation, and does it have much to say about potential benefits or downsides?
Yeah, it's a good question. So I suppose what I'm most familiar with are because when you're sort of talking about the intersection of sleep and meditation here, that there are studies of the practice of meditation and mindfulness for improving sleep, and there are certainly indications that that these practices can help with things like insomnia. I've also seen other studies that show that meditators actually spend more time in deep sleep and REM sleep. So, and so I think that there's some evidence. It's not a huge amount of literature that meditation and again mindfulness practices can improve sleep, and particularly things like insomnia. And I guess there's a certain intuitive appeal there, right? I mean, your mindfulness and meditation, one of the things you're doing is sort of just generally calming the soul and addressing things in a way that or things that might be creating a challenging environment for the individual on a day-to-day basis, anxiety and worry and things like that. And of course, these things do drive insomnia. And so to the extent that meditation and mindfulness can perhaps moderate those other more negative emotions, I completely see how they could improve sleep. So I would definitely, even without a lot of data to point to, be able to get behind. And it's hard for me to, in a sense, scientifically get behind things I don't have a lot of data for. I could get behind the concept of meditation and mindfulness being good for sleep and good for getting good sleep. But I think that's about as much as you're going to get in terms of the intersection of the two.
Yeah, sure.
So, yeah.
I thought we could briefly talk about dreams. So do we have some idea of the role dreams play in sleep? Or is it still a mystery?
Right. So, I think it's important for me to acknowledge where I do have expertise and where I don't.
Sure.
And I'm not an expert on dreams, but of course understand the fascination with dreams and interpreting dreams. I mean, there's something almost really mystical about dreams, right? You hear stories of people having scientific breakthroughs, or composing a new song, or having some profound moment of insight in their dreams. So again, it's hard not to appreciate the fascination there. But my take on dreams is they are likely a piece of the long-term memory formula or formation puzzle. So and dreams are when the brain is attempting to create a coherent whole or coherent representation of reality from lots of essentially disparate pieces of data accumulated during the day. But even there, I think I'm speculating a bit more than I'm comfortable doing. So I'll probably stop here with the dream talk, just as a matter of retaining credibility.
No problem.
Okay.
We can move on to more solid ground.
Sure.
So here's some solid ground that I'm sure you're quite well versed in, and that's neurotransmitters themselves and hormones. So we have a bunch of neurotransmitters and hormones that affect and regulate our waking and sleeping states. So I wonder if we could do a brief overview of a few and how they affect the body in relation to these sleeping and waking states. So sure. Maybe we could start with, I might get the names of these wrong. I'm not, but
give it a whirl.
I'll give it a whirl. Is it acetylcholine?
You got it. Yes. Right. Acetylcholine. Yes. So sure. And you would like me to talk a little bit about that?
Yeah, I've got 4 or 5 here, so maybe we could just do a brief overview and how they affect the body, and then maybe we get a little bit deeper into some of their functions.
Got it. No problem. That sounds great. So, and yes, this is territory I feel quite comfortable in. So, to the extent I can draw upon fact, right? So, acetylcholine is a neurotransmitter, as you identified a moment ago. It's actually used by both the central and peripheral nervous systems. So, in the peripheral nervous system, it's the transmitter that motor neurons use to communicate with skeletal muscle tissue, as well as what we call the autonomic sort of vegetative part of the nervous system uses. Although the autonomic nervous system has two branches, a sympathetic and parasympathetic branch, they use acetylcholine in slightly different ways. And so it might be worth pointing out that some poisons or neurotoxins actually act on acetylcholine neurotransmission, including and more specifically on its degradatory enzyme, which is called acetylcholine esterase, to produce their negative effects. So things, and this is just things you and your listeners will be familiar with: botulism, Black widow spider venom, VX nerve gas, some pesticides. They all actually produce their effects, which clearly are often fatal, by disrupting aspects of acetylcholine function at the neuromuscular junction. But actually, in somewhat striking contrast, low dose acetylcholinesterase inhibitors can be used clinically and are used clinically to help with various diseases such as Alzheimer's or a disease called myasthenia gravis. So now in the brain, which is more where this whole conversation is taking place, acetylcholine is used also used as a neurotransmitter too, but arguably it's more of a neuromodulator in the sense that it tends to be released with other transmitters. So loss of brain acetylcholine, particularly that which derives from basal forebrain neurons, it's an area of the brain that I am very interested in, is actually long linked with Alzheimer's disease. So, and there's interestingly enough, there's a series of studies, I suppose, linking basal forebrain acetylcholine to the waking process, and some have argued that loss of acetylcholine might explain some of the sleepiness seen in Alzheimer's patients. But we actually have some data, we've published it recently, which would suggest that these neurons actually don't promote via release of acetylcholine wake or sleep per se, but rather may play a more important role in sort of suppressing, that slow wave activity I talked about, basically keeping that slow wave activity from intruding into wake. In other words, these neurons, these acetylcholine releasing neurons, don't drive wake, but they do contribute to sort of the quality and level of wake.
Okay.
So it's kind of a brief overview of acetylcholine.
Brilliant. Next on the list is GABA, which is gamma aminobutyric acid.
You got it.
I got it right.
You're on a roll, Ryan. Okay, cool. So GABA is in fact the brain's major inhibitory fast neurotransmitter, and GABA or GABA releasing, and for that matter, GABA receptive neurons are literally found, all over the brain and play truly a myriad of roles. So, GABA neurons in the basal forebrain and preoptic area and brainstem are actually thought to play major roles, very major roles, regulatory roles in producing and maintaining both wake and sleep. And so I guess it wouldn't come as any surprise for you, given what I just said, to hear that in the context of sleep drugs, those that facilitate GABA inhibition, so drugs that are, there's a group of drugs called benzodiazepine receptor agonists. These are actually used as first-line pharmacologic therapies for treating certain sleep disorders, in particular insomnia. And these drugs would include things that I'm sure you've heard of, like zolpidem and temazepam.
Sure.
And there's actually other drugs that act on these same receptor, which would include barbiturates and then alcohol, in fact. So, but back to the benzodiazepine receptor agonists, they're actually very well tolerated, and they have very few safety concerns when appropriately dosed. But the downside to these drugs, when used either in the short or the long term, include a slightly amnestic effect, and that's really the inability to form memories after drug consumption. Some residual sedation. So, in other words, taking the drug, getting a good night's sleep, waking up the next day and just kind of being groggy, kind of almost defeats the purpose of taking the drug, I suppose. But then you have, we worry about these drugs in the elderly because they can make people feel a little bit unsteady, so they can fall. Falls in the elderly are always a big concern. Broken hips, broken bones, and then finally, these drugs have what folks tend to call discontinuation effects, and that means you basically stop taking the drug and then you get a rebound. So, for example, if you took the drug to go to sleep because you had insomnia, it works for 3 nights. You stop taking it, you get a rebound insomnia, and then I guess like any other drug, there's a concern there'll be development of physical or behavioral dependence. And one thing that it might be worth mentioning too for the listeners is that there are also case reports. They're possibly exaggerated in one way or another, but of people taking these drugs and having these parasomnia-like behaviors when taking the drugs, and that includes things like sleepwalking and sleep eating and sleep driving, seriously sleep driving, and amnesia. So I'm just trying to think here. Oh yeah, another interesting thing about these, again, benzodiazepine receptor agonist drugs is that while the user tends to experience better quality sleep and increased sleep time, there is actually a reduction, this is very interesting, in the deepest stages of sleep, which is the state of sleep that we tend to think of as being the sort of truly, in quotes, restorative state of sleep. So for me, that it remains a bit of an open question as to whether the reduction in deep sleep is real, or if it's just the case that one effect of this drug or these drugs is to modify, these cortical features of EEG. In other words, modifying the features we interrogate on the EEG, which, as we discussed earlier, is what we actually measure. So for example, do these drugs affect the production of delta waves, which are the surrogate measure of deep sleep, but maybe not affect deep sleep per se? So hard to say. I mean, I guess what you and a savvy listener might infer from what I just said is that, delta waves themselves, perhaps they're epiphenomenal to the sleep process.
Yeah.
I think that's an intriguing, if completely controversial conjecture on my part. So there you go. I've just gone down the path of speculation. That's GABA. That's sort of it plays a very fundamentally important role in sleep and wake. And again, the drugs that are used as first line therapies for most sleep and wake problems involve a drug that interacts with this GABAergic system in the brain.
Now, you did some experiments. I did a bit of Googling, and I found that you did some experiments on remotely activating neurons in the parafacial zone, or the PZ, of the brainstem. And those were specifically neurons that manufacture GABA. And I wonder if you could briefly explain how you managed to so precisely control these neurons and the effect it had on the animals when they were turned on, because I found it very fascinating.
Oh, okay, cool. Yeah, well, you did a good job Googling. And so, we used a few genetic tricks to make this happen. Okay, so in brief, and this goes back about 5 years now, we used a viral vector to get a gene to express selectively in GABA releasing neurons. And that's when actually she mentions is important. Almost all neurons make GABA. Not all neurons can release GABA. So these neurons that we target can release GABA. And the reason for that is because GABA is used sort of metabolically within the cell, in addition to being a neurotransmitter. So, but anyhow, we expressed this gene selectively in these GABA releasing neurons of the parafacial zone, which is a region of the brainstem we had previously shown to be involved in sleep regulation. And so the gene itself encoded a receptor system that interacted with a pharmacologically inert ligand that we would administer to in this case, a mouse. So you can think of it as kind of a key and lock system that we put together. So we didn't really create the system. It was actually created by a scientist, a guy named Brian Roth. What we did is we simply put the system into a viral vector so we could actually get it into specific areas of the brain. And when we activated this receptor vis-a-vis the administration of this ligand, the mice fell like near instantly to sleep. It was really cool because you have literally 1 minute the mice are wide awake and walking around, the next minute they're sound asleep and expressing just bucket loads of slow wave activity in their EEG. And the system was remote control in nature, so we could trigger on demand. And so in other words, we weren't giving a drug that was causing the brain to do anything. We were just activating the receptors. So at any time of day, we'd activate the receptors, and the animal, even not having any quote unquote sleep drive, would go right to sleep. So as it turns out, we've used the same system. It's actually called chemogenetics, by the way, to activate other cell types in other regions of the brain. I'd say at least 20 different cell types and regions of the brain at this point. And we've never reproduced this sleep effect, highlighting just how unique the parafacial brainstem region is in producing this natural sleep. But I probably should note that more recently, others have used the same system and another remote control system you've probably heard about called optogenetics to activate a group of cells in the preoptic region of the brain, and shown that these cells can also drive sleep. And likely there's a big role for GABA there too.
So could this method be something useful in the future for insomniacs?
Yeah, theoretically, yes. I mean, I think we have a long way to go for to translate this to sort of the human condition. But yes, theoretically, this system will work quite nicely in humans. We may need to play around or tinker with the ligand a little bit. The ligand is clozapine oxide, which is something that in humans can actually back metabolize a little bit to clozapine, which is basically a neuroleptic, and so that's not a good thing. But there's every reason to think that we can, the folks that are engineering these systems can come up with other, lock key systems that would work well in the human condition. So, to give you one example, I don't want to get too far afield here, but I have we had engineered another system that allowed us to inhibit neurons in the brain, either specific type of neurons or just sort of globally. And I have some colleagues that are now using this system in the context of actually both Parkinson's disease as well as epilepsy. And the idea is that by giving people a pill for this particular drug, and what's nice about this other system, which I'm afraid I apologize for not going into too great a detail here, but
go for it.
Well, the drug itself is actually already in routine use in human and veterinary medicine. So it's beautiful, right? You can just start taking the drug, and it's only going to act on this receptor, which is not normally expressed in the human brain. It actually comes, believe it or not, comes from worms. And so the idea here is that you could get this channel into the brain. So, like, say, for example, the medial temporal lobe of an epileptic, or into the midbrain dopamine system of someone with Parkinson's, and actually inhibit these neurons, which have become essentially overactive, and by taking this pill, and treat them. And so I think there's a lot of excitement. People are actually have moved this to the next stage, doing this pilot work in non-human primates. And I wouldn't be surprised if in 5-10 years we've moved fully into a preclinical mode with human trials. So yes, tremendous translational potential. I just want to be clear that I don't think it's going to happen tomorrow, but I'm excited that conceptually it appears we can move forward all the way to the human clinical condition. So
regardless, exciting stuff.
I think so, but I'm biased.
Sure. You mentioned dopamine there in the Parkinson's, so why don't we move on to onto dopamine?
Sure. Okay, so dopamine is actually a bit of a complicated story. Dopamine it's because it plays a number of important roles in neurobiological regulation, right? It has a role in so many things. And
but when we're talking about biology, I suppose we're always going to be that disclaimer. So. Yeah.
Right. So, but when it comes, we can bring it back down to wake and sleep, because when it comes to wake and sleep, the primary role of dopamine seems to be one of wake promotion, right? So most drugs that increase wake, okay, like things like whether they're street drugs or clinical drugs, so amphetamines, amphetamine-like compounds, modafinil, bupropion, mazodol, they all involve potentiating, in other words, enhancing dopamine transmission in the brain. So I think that's kind of the dopamine story, is that it produces wake. There's drugs that can selectively that act on the dopamine system in one form or another. They can block a dopamine transporter, keeping dopamine, for example, in the synaptic cleft for a longer period of time, somehow inhibiting its metabolism. That produce that produce wake. So I guess, but that's about as much as I could really say about dopamine in this particular context.
And coffee would presumably fall into that category as well, to some extent.
Yeah, certainly. So it certainly falls in the category of wake promotion. Absolutely. So caffeine, or coffee, right? So what's in coffee? Well, it's caffeine, and it's clearly the most popular stimulant in the entire world, and at least for most people, right? And so, caffeine, how caffeine works. And so I'm coming back to caffeine because that's the psychoactive component of coffee, right? So,
sure.
So caffeine produces its effects by blocking the ability of a little molecule called adenosine from binding to its receptors in the brain. And adenosine is an interesting little molecule because it accumulates in our brain during wake. And so the longer you're awake, the more adenosine you have basically floating around. And what adenosine does is it inhibits neuronal activity to eventually produce sleep, or at least feelings of sleepiness. So if you block adenosine from binding to its receptor, which is exactly what caffeine does, adenosine is no longer effective at producing sleep. So people use caffeine to great effect. People are very addicted to caffeine. It has all kinds of wonderful properties. Actually, one thing, speaking of tangents, that you and your listeners might find interesting is that some people, including some I know, swear by these so-called caffeine naps, okay, which involve basically imbibing some caffeine, typically in the form of coffee, of course, then power napping for 15 to 20 minutes. So the idea, or I guess working principle here, is that it takes about 15, 20 minutes or so for caffeine to begin exerting its wake-promoting effects in the brain. So if you time the intake and the nap just right, one can theoretically come out of the nap just as caffeine's taking effect and really minimize any sleep inertia and maximize wake drive. So I've actually not tried this myself, mostly because I don't actually drink coffee or, generally speaking, take naps. But again, those I know who have done this actually swear by it. So anyhow, you can give it a whirl sometime if you want to try it.
I have tried it, actually. And
does it work for you?
The times where the nap actually becomes anything resembling a nap, it works quite nicely. But sometimes it takes a bit longer than 10 minutes to
actually fall asleep.
Yeah, yeah, exactly.
Well, Ryan, that's a sign though that you're good, that you're well rested, actually, which is a good thing.
Most of the time, at least.
Right.
All right. Well, the next one that we could talk about is melatonin.
Oh yeah. Okay. So melatonin, it's a hormone produced by a little gland in the brain, actually, pineal gland, and it's an interesting little hormone. It's secreted only at night, and in fact, its release is actually suppressed by light exposure. So the efficacy of melatonin to improve sleep in insomniacs, which is really how it's been sort of touted and used, is a bit mixed, frankly. But it does seem to offer some benefits to sort of specific patient cohorts, in particular individuals diagnosed with certain circadian rhythm disorders, such as something called delayed sleep phase disorder. But I personally find the evidence for a truly sort of quote unquote hypnotic effect of melatonin somewhat underwhelming. It's interesting to note, I suppose, that melatonin is only associated with sleep in diurnal mammals like us humans, because in other nocturnal mammals, melatonin is actually elevated during the wake or active phase. So that's just a interesting little tidbit, I think. And so when one's making these great claims about melatonin being this wonderful soporific or hypnotic compound, I find the data again kind of underwhelming, but also I tend to point to sort of the comparative physiologist out there, the comparative physiology out there, and say, well, if it's so potently wake promoting, why is it not promoting? Why is it not actually driving sleep in more than half the animals on this earth? So evolution tends to be fairly conservative in certain ways, right? So
yeah, sure.
Anyhow.
That's very interesting. I never knew that about the sort of nocturnal animals.
Right.
So that brings, how safe do you think exogenous melatonin is, and would all brands be equal for people that I have some friends that have tried it and swear by it, and I was always kind of on the fence, but I'm just curious how safe you think it would be, and whether all brands or all sources would be equal. I suppose that just depends with any supplements. You just have to do your own research and make sure it's independently verified and everything like that.
Yeah, no, I think you're spot on. I mean, so I can tell you that melatonin consumption in doses of up to about 10 mgs are likely safe. I say this because these doses have been used in human studies without any particular side effects reported. You go higher than that, you can start to see people get headaches and feel dizzy and have other, I suppose, disabling symptoms. But it's also important to bear in mind that the physiological dose would be closer to 0.1 mg. In other words, several orders of magnitude less than what you'd be taking with those off the counter, over the counter pills. So and finally, to your point, melatonin isn't a regulated product, right? So it's really anyone's guess as to whether or not your melatonin pill contains the dose listed. And frankly, it's anyone's guess is if it even contains melatonin or simply grass clippings or something. So,
Yeah, sure.
It's not a supplement factor, because I think there's a lot of really great supplements out there. It's just that you just don't know. So you're right. You have to do your research, look into your source. But no, I think if you keep it under 10 mgs, you're fine. And I don't want to discourage anyone from necessarily taking it. I just I can tell you when I'm kind of wearing my science hat, I view melatonin through something of a jaundiced eye here. I'm not I'm not a going to get real evangelical about taking it. I just I have a hard time viewing it as a really potent hypnotic. But again, the other thing, Ryan, is placebo effect is very, very powerful. We're seeing more and more of that. I mean, if someone thinks it's helping, great, take it.
Absolutely.
Even if it's not the melatonin, you think it's the melatonin, great. You're getting better sleep. So we can't discount placebo effect on some of this stuff as well.
Absolutely. So one last thing on melatonin. I mean, for those that aren't aware, but artificial blue light affects melatonin production and inhibits the production of melatonin. And there have been a number of companies that have sprung up to sort of intervene with this and help people get better sleep. And one of these is software called Flux or Flux. Are you familiar with this, with software Flux?
I am, yeah. So go back to the artificial light. I'll come back to Flux here. Or Flux. So you're absolutely correct. Artificial light at night does, as I said in caps, affect melatonin. In fact, it completely suppresses its release. So light is incredibly potent. Specific wavelengths of light, in fact, are very, very potent at suppressing melatonin. And so this fact has been used, at least in part, to substantiate the claim, and again, I suppose you could say also provide an explanatory basis for why reading your iPads and otherwise looking at your computer screens, all of which are enriched in wavelengths of light that maximally suppress melatonin, hinder the sleep process. So what one could actually think of light, in particular blue light, so shorter wavelength blue light exposure in the later evening hours, is acting a bit like electrical caffeine. I mean, it really keeps the brain activated and melatonin suppressed. So both of which would, I suppose you could say, are somewhat anathema to actually falling asleep, right? So, but software or apps that filter blue-green wavelength at night, like Flux, are actually a good idea. I mean, if you're going to use your light-emitting screens, or something that has a light-emitting screen like an iPad and so forth, I think that they're a very good idea. And actually, one doesn't have to use the software. You can actually, it's as simple as wearing, it may look a little silly, but you can wear glasses that are blue wavelength blocking glasses, and so you'd wear those while you're reading your computer screen. It would have the same effect as the software. So yeah, I subscribe to the concept of minimizing the amount of blue-green wavelength light at night, because again, it's going to do two things. It's going to activate your brain, and my colleagues won't love that I phrased it that way, but it really does produce. You can actually see higher frequency EEG begin to show up even when you're getting drowsy, and it will suppress melatonin. And again, both of those are somewhat the opposite of what you want to do if you want to fall asleep.
Sure. So one would presume that Bono might be perpetually tired then.
Well, perhaps if he's blocking the blue light all day long, yes, he might be. But he sure looks cool.
He does look cool.
I can't knock the man.
Can't knock him. So there's a fun little section of the brain called the hypothalamus, which regulates body temperature, hunger, thirst, fatigue, sleep, and circadian rhythms. And within the hypothalamus, there's a thing called I may get this wrong, suprachiasmatic nucleus, or the SCN. And I wonder if you could define what the
suprachiasmatic.
Sorry, say it.
So I said suprachiasmatic. Yes.
Suprachiasmatic nucleus. we'll keep it at the SCN.
Let's go with SCN.
Yeah,
SCN,
cool,
yes,
cool.
yes, yes.
So I wonder if you could define what the SCN is and the role that it and the hypothalamus play in our sleep regulation.
Yeah. Okay. So great question, and you're spot on. But maybe I'll take a quick step back and talk for a second about circadian biology, which is the field of study that that seeks to understand how and essentially why our biology is temporally organized. So in other words, why do we do certain things at certain times of day, right? Like wake and sleep, and why do important physiological and behavioral measures such as hormone levels and physical performance and cognitive performance and so forth exhibit a 24-hour rhythm of a rather high amplitude rhythm in some cases. So as it turns out, and as you correctly noted in your question there, we have a little biological clock in our brain, and this so-called master circadian clock is actually a collection of really tiny and tightly packed neurons located in, again, as you rightly noted, in the hypothalamus. And the structure itself is called, as you described, suprachiasmatic nucleus, or SCN. And so the SCN occupies maybe 3% of the total volume of the hypothalamus. And so to give you a sense, in humans, the hypothalamus itself is about the size of an almond. So, you're talking about a structure that's 3, maybe 5% the total volume of that almond. That's in our brain. That's where our clock is. And from a biological standpoint, this clock is really incredibly remarkable, and for many reasons. But perhaps most, I suppose, notably, that really no other region of the brain can assume its function if it's actually if it's damaged. And we know that the clock's fundamental role is to keep us synchronized with the Earth's light-dark cycle, as well as so we have an external synchronization, as well as keep our body's internal rhythms synchronized with one another. And the clock does both. It provides for internal synchronization and external synchronization. And being synchronized to the external light cycle is incredibly advantageous. Or perhaps I should say adaptive, because it allows for predictive rather than simply reactive biological regulation. And I guess you could say, well, what do you mean by that? Well, by way of example, before we wake up in the morning, our metabolism starts to rev up, our body temperature begins to increase, our nervous system starts to show increased activity, and this is all in anticipation of the increased energetic demands of the day. And this isn't just a great big hypothesis. We know that proper external and internal synchronization is truly fundamental to our physical and mental well-being. So I guess a great example of what happens when your internal rhythms become transiently offset or desynchronized from the environment, as well as with one another. In other words, when our external and internal synchronization is off, you see that in that disorder, jet lag disorder. So you're probably familiar with jet lag, because it's something that most of us who have taken any form of long haul airplane flights, which I think you've done recently, Ryan, have experienced.
Oh yeah, and 30 hours will do it to you.
Yeah, you're exactly right. So then this results. It kind of varies from individual to individual, but both sort of the amplitude of the symptoms as well as the scope of the symptoms. But it generally involves things like fatigue, loss of appetite, insomnia, irritability, gastrointestinal disruption, and certainly cognitive impairment. And often people just say, I just feel crummy, general malaise-y sort of feel. So and some individuals experience jet lag on a chronic basis. So basically, can you imagine living your life basically chronically jet lagged? In certain occupational settings, you see this. Shift workers, long haul airline pilots, astronauts, people that have actual sleep disorders, circadian rhythm sleep disorders. And so, or specifically one called circadian rhythm sleep disorder, and the physical consequences of this long-term disruption may reach, far beyond just feeling miserable, right? Because these individuals are at a demonstrated increased risk for developing cardiovascular disease, metabolic disease, things like diabetes and obesity, and even some types of cancer. So it's really not an exaggeration to say that this little clock, this little suprachiasmatic clock, is kind of an inescapable and all, I suppose, pervading biological consideration when it comes to our health and well-being. And so to go to sort of the last part of your question there, it probably comes as no surprise that the circadian clock also controls the sleep-wake cycle or sleep-wake rhythm. As is self-evident, I suppose we sleep at night and wake during the day, at least for those of us working a normal, that is not shift or nighttime schedule. And the circadian clock plays a really critical role in determining the timing at which we wake up and the time at which we fall asleep. And the clock also plays an important role in helping us actually stay awake during the latter part of the day, as well as helping us keep or stay asleep for the entire night. In other words, it kind of provides it helps us have a continuous bout of wake during the day and a continuous bout of sleep at night. So at different times of day, you could think of the clock as providing a wake promoting or sleep promoting influence on the body and brain. And Ryan, because we're talking about rhythms and the circadian clock here, I would be remiss if I didn't note, and you're likely aware that the most recent Nobel Prize in physiology or medicine was actually just bestowed on 3 circadian biologists for their work on the molecular mechanisms of the circadian clock, which I think really highlights just how important this field of study is to biology and medicine. Yeah.
And presumably most multicellular organisms would have some sort of a clock as well.
In fact, we know all eukaryotic cells, all eukaryotic organisms have circadian clocks, and there's even evidence of some timekeeping, 24-hour timekeeping in prokaryotes, unicellular organisms. It's fascinating. Wow. It's a cross phyla. Mm-hmm.
Wow. So, man, that's brilliant. I thought we could talk a little bit about monophasic, biphasic, and polyphasic sleep. Anthropological studies have suggested that non-industrialized societies demonstrate a significant difference in sleep patterns compared to us in the West, with segmented sleeping patterns quite commonplace. And similarly, it's been hinted at by people such as Roger E. Kirsch that sleeping in a single session is a relatively recent phenomenon brought about by industrialization and artificial light. And then we also have, I think his name is Michel Siffre, his cave experiments in which 2 people stayed in dark caves for months at a time, and their sleeping patterns fluctuated to such a degree that one subject sometimes slept for 30 hours at a time. So I wonder if you could explain the difference between monophasic, biphasic, and polyphasic sleep, and whether we know very much about the pros and cons of the different patterns.
Sure. Yeah. So this is actually a fascinating question, and probably one we could spend a couple hours on. But it's also one that remains unanswered, and if even a bit contested. So I like to go back to historical writings. I mean, Homer wrote in the Odyssey, in his first sleep, call upon your heartiest cheer. It's which we all sort of interpret as a likely reference to segmented sleep that was practiced at that time. And and if your listeners are unaware, the basic idea here is that we, as members of post-industrial societies, by and large, consolidate our wake and sleep to one, continuous event, or 2 continuous events, I suppose, during the 24-hour day, as we just described a moment ago with the circadian clock. Now, taking a nap, including a cultural nap like a siesta, but otherwise having a long, and the key word here is consolidated night of sleep, still falls under the heading of monophasic sleep. But but it has been argued, and you correctly noted, and argued, I guess, most elegantly and perhaps strenuously by the historian Roger Icker, is that before the Industrial Revolution, historical or typical sleeping patterns for humans were possibly biphasic. That is to say, people went to sleep for maybe 4 hours. They woke up in the middle of the night for maybe 2 or 3 hours. This is the time of night they engaged in writing, reading, praying, sex, etc., and then went back to bed for another 4 hours. And so, not only is the historical evidence for this quite strong, but this pattern of sleep is arguably more similar to that of other animals, and evolution tends to, as I said a moment ago, use a good thing over and over. Others, though, have argued that these patterns of sleep were perhaps only seen during the long nights of winter or days of the year with so-called short photo periods. And as for Michel's cave experiment, this has long been a head scratcher for me. Frankly, his subjects aside, if you look at his own sleep patterns, they were actually remarkably normal and certainly circadian in appearance for the first 2 months of his time in the cave. He then self-admittedly became very depressed, almost despondent, and this is when these super long sleep-wake cycles appeared. I think what he did was fascinating, but I also think there were far too many uncontrolled variables to draw any specific conclusions on his body of work. And again, this is me, as I said a moment ago, wearing the scientific hat, walking the road of systematic doubt. Okay, so
Sure.
But on the other hand, in the early 1990s, it may have been around 92, another scientist named Thomas Ware actually tested this sort of short photoperiod sleep hypothesis by confining a group of humans to a room in which they were exposed to a very relatively short photoperiod. I think it was 10 hours of light and 14 hours of dark. And he found that his subjects eventually adopted a biphasic sleeping pattern. But another I think final kind of consideration in all of this is where we, that is the human species, evolved, right? We more or less, it was near the equator, which has a consistent year-round 12-hour light, 12-hour dark, and then our species just sort of in this, amazing diaspora spread to all distant corners of the planet. In some cases to latitudes that are almost completely dark much of the 24-hour day during parts of the year, and almost completely light during much of the day during other parts of the year. So it's hard to say what is or isn't our natural, quote unquote, sleep pattern. I should mention a very interesting study by Jerry Siegel and colleagues at UCLA that was recently published in Current Biology, which by the way is a great journal. If you haven't read much out there, I would encourage you to. It describes their attempts to measure sleep-wake cycles in 3 different pre-industrial societies. And so in today's world, that's not easy to find, but they actually did. And what they found was that all 3 societies showed similar sleep organization amongst themselves, okay? And none showed a biphasic sleep pattern. That is, and by that I mean they did not exhibit an extended period of wake in the middle of the night. And so Siegel and his colleagues concluded that these sleep patterns in these pre-industrial societies were most likely characteristic of pre-modern day Homo sapiens. So, food for thought. So, I guess I would note just more personally that biphasic or polyphasic sleep is not something I find myself doing naturally, which tells me that at least for my biology, which seems to track more or less with that of most of my friends and colleagues and contemporaries, is monophasic. I simply don't wake up in the middle of the night, nor do I feel tired upon waking, at least not until the end of an active day. So it's interesting, it's fascinating. I think trying to though make the claim that one type of pattern is in fact the default evolutionary pattern over the other. There's pretty good arguments that can be made from both sides, right? So, but going back to Jerry Siegel's, it was a modern day study done by a modern day sleep investigator or contemporary sleep investigator in societies that are again, as close to sort of pre-modern day Homo sapiens as you're going to find, sure. And there was no evidence there of biphasic sleep. So
interesting. Because there are these groups that are very passionate about polyphasic sleep. I believe there's a few societies floating around the internet, and they give the different techniques and they tout certain pros and cons. So I was just kind of curious if is the jury still out on whether biphasic or polyphasic is quote unquote healthy or not, or has any kind of benefit? Or
I think the jury is certainly out again on what is actually our default pattern, right? So, I think if we had crystal clear evidence that biphasic was what we have always done, then we might actually, as a society, consider trying to adopt that, right? It makes sense, and it's what your brain wants to do. And there's probably a good reason for that. But in terms of one of these sleep patterns being detrimental to one's health or otherwise more advantageous to one's health, I have to go with the jury's still out. I think if as long as people are getting the sleep they need on the 24-hour day, and they find, and a given individual finds that the polyphasic approach works better for his or her biology, and in fact they can accommodate polyphasic in their. I mean, I don't think I could do polyphasic, just simply the nature of my of my day. And between having a toddler and a job where I have to be at during the day, it would be kind of hard to go polyphasic. But who knows? Maybe when I retire, I'll which I'm not sure that's ever going to happen. But if I do, maybe I'll try it out.
Yeah, I mean, it seems like it'd be quite an exercise in scheduling, wouldn't it?
It does. It almost seems like more than I want to take on scheduling. I think you hit the nail on it.
Yeah, for sure.
I'm just following the lead of my brain, if you will. It says I'm tired, I go to sleep.
Yeah. Well, some people have suggested cycles of hot and cold showers in the evening or exogenous blue light in the morning as ways to sort of modulate or hack the circadian clock. Do you know if there are any methods that you could hack it quite immediately? For example, somebody that could be really tired, still really awake in the evening, and they need to fall asleep as fast as possible. Are there any of these sort of temperature modulating methods that you know of that work? I've heard about them, but as I say,
well, like you, I've heard about them. I've read with some great interest, and so sort of being I guess in some respects a physiologist by training, I think in terms of temperature regulation and other things. And so to start with, I think that blue light in the morning is potentially a good hack, quote unquote, insofar as it matches with the natural spectral content of the rising sun, and thereby should reinforce, for lack of a better word, what the circadian clock is trying to achieve. The idea of hot and cold showers, that really derives from, I think, the body of literature that has shown that body the work that has shown that body temperature tends to drop as we go to sleep and rise as we are waking in the morning. And so I guess where I was going with this was appropriately timed and appropriately calibrated in terms of temperature. Showers could, in theory, facilitate both processes. So, our temperature rhythm is interesting, right? It integrates all aspects of our physiology, and so this hack might be a useful one for those wanting to hasten time to sleep or to wake. Somewhat, I guess, relatedly, I've seen a study where individuals with insomnia were given head cooling caps, brain cooling caps, I think they called them, and these caps seem to have rather dramatic effects in reducing the time to sleep. So, including in true insomniacs. So, yes, I think these are potential hacks, though I'm not sure I would say the hack is to the clock itself. Honestly, it might rather be to downstream elements that the clock controls. But speaking of tangent, and both of us having a penchant for those, there's a variety of interesting hacks that involve at one level or another the clock that are used in non-human settings that you might find interesting. Like one, I think, cool example is that, in the world of horse racing, it's ideal to have your foals be born close to the beginning of the year, since thoroughbreds are raced by age. In other words, you kind of have the oldest guy in the group when they're racing, for obvious physical reasons. And so, but the natural breeding cycle of horses means they tend to only be reproductively active, the mares, that is, during late spring or early summer, which is too late for a January 1 born foal, given the 11 to 12 month gestation period of a horse. So, but by putting the horses and the mares specifically on blue light enriched longer day schedules, this actually influences the activity of the SCN, suppresses melatonin production, and the net result is that mares then can breed much earlier in the year. They end up giving birth to foals closer to the first of the new year, and again, that essentially ensures that these foals are always among the oldest and hence most physically robust in their racing group. Anyhow, I thought you might like that as
some smart cookies
involving the clock and melatonin. Yeah, right.
Yeah.
So
I've got a little slight curveball which is vaguely related to this, and it's
sure.
I don't know, it was a question from a friend of mine who's part of the podcast, and he asks, is it possible to fall asleep immediately at will? He likened it to a kind of a superpower.
Yeah, well, interesting question. Well, I mean, yeah, if you're really sleep deprived or have an untreated medical condition like narcolepsy, yeah, it can happen very rapidly. But if you're not sleep deprived and you're in the middle of the day, it's nearly impossible, if impossible, I suppose, in large part because the brain milieu. We just talked about this cocktail of neurotransmitters that cocktail is not organized for sleep, and also because the circadian clock, which of course we were just talking about, is providing a rather potent alerting influence during most of the day. So to fall asleep immediately, I would say it would you if this was happening to you, go see a certified sleep physician, because you probably have a sleep pathology. Yeah,
I think I'm thinking it was more along the lines of a sort of a technique.
Yeah. Unfortunately, no. You really, particularly during the day when everything is, and by everything I mean, the neurochemistry and the circadian clock, everything is pointing you in the wake direction. To overcome that, in other words, achieve instantaneous sleep, you would either have to, you'd have to just be sleep deprived, basically, to get to that point.
Yeah.
Be able to do that quickly. Yeah.
Or we wait for your parafacial zone sleep switch to become
That's right.
safe for human use.
Exactly.
Okay. We can wait for that. That's okay. All right. Well, I think we're coming to an end now, and I realize you've got to get back to the vast amount of work that you're involved in. So,
well, if you had a few more things to cover, if you would like, I can probably do another 15 minutes. So it's up to you, Ron.
That should probably cover the rest of what we got here. So that would be nice. Where are we now? So, I thought this is probably a good time to get into sleep hygiene, the definition of sleep hygiene, and yeah. Sure.
So what is sleep hygiene? Well, the idea here is what can one do to optimize their ability to achieve good sleep, and so this would involve, in some order, adopting and maintaining a specific time to rise in the morning. I want to emphasize that point, and go to sleep at night, and really not deviating from the schedule on the weekend, at least to the extent possible. Getting 7 to 8 hours of sleep every night, avoiding stimulants after the early afternoon, keeping alcohol consumption in the evening to a minimum. If you're going to drink, and there's certainly compelling data to suggest that drinking in moderation, 1-2 drinks per night, in fact, reduces all-cause mortality. So it's a perfectly good thing. And I would suggest having your drink with dinner, because this tends to slow the absorption of the alcohol and allows for metabolism of the alcohol before you fall asleep. Ideally, you want to sleep in a dark room that is at an optimal temperature. That would be typically the low to high 60 degree in the Fahrenheit. Sorry, I'm doing Fahrenheit, but and I would advise people to stay off their electrical devices or electronic devices at least an hour before bedtime, for reasons we discussed a moment ago. And if one has to be on their device routinely before bed, I would suggest they use the dimmest screen possible, and consider getting like the FLux app that reduces the blue light emission. And why I was emphasizing the part about getting up at the same time every day is because it goes back to the circadian clock. If we shift our bedtimes and wake times daily, or as more often is the case on the weekends, this is actually very disruptive to our ability to consistently achieve a restful night of sleep. You end up fighting your clock, and the clock will always win, right? So, and one other thing I'd point out is, I get asked this a lot. Say, hey, well, why 7 to 8 hours, right? And there's a lot of people who just feel like they don't need 7 to 8 hours. Well, my response is I try to, again, be data-driven in my responses. So if you look at joint consensus statements of, at least from the American Academy of Sleep Medicine and the Sleep Research Society, this was generated by a panel of expert sleep physicians and researchers reviewing over something like 5,000 or 6,000 studies. The recommendation was that adults aged 18 to 60 should obtain at least 7 hours of sleep per night on a regular basis to promote optimal health. So in a nutshell, the data shows that all-cause mortality is decreased for those sleeping in the 7 to 8 hour range as compared to those sleeping 6 hours or less. And they were actually able to, with this data, make specific linkages between insufficient sleep and negative outcomes in terms of cardiovascular disease, metabolic health, so type 2 diabetes, for example, depression, immune responses, and cognitive and psychomotor performance, some types of cancer, as I mentioned earlier. So all of this said, and as I said in other discussions, I'm truly not in the business of selling sleep or otherwise, fear mongering over sleep loss. But so my take home is, and always is, that we should all try and optimize our sleep. And part of that optimization, if the data is telling us, means getting 7 to 8 hours of sleep per night. But also not to necessarily lose sleep over the occasional inability to get good sleep, including that 7 to 8 hours, because that happens to all of us.
Mm-hmm, mm-hmm. Did the research that you just mentioned have anything to say about longer periods of sleep?
Yeah, actually, it's an interesting question, right? So there was actually a bit of an inflection, almost a U-shaped curve here. When you started to go into the 9-hour range, you actually saw what you saw in terms of outcomes, what you were seeing in the cohorts that are sleeping 6 hours or less. In other words, 7 to 8 hours is very much a sweet spot. You start to go into the 9+ hours, you actually start to see an increase in these negative outcomes. So it's hard maybe to fully explain, but that's what the data is telling us. That's what the studies are telling us. And so, in other words, getting too much sleep might not be quite as bad for you as getting too little sleep, but it's certainly worse than getting optimal sleep, which again is in the 7 to 8 hour range.
That's very interesting.
So it's a great question.
Yeah. Would you recommend any kind of supplementation for sleep? People using, as you said, benzos, and there's all sorts of sleeping aids and sleeping pills for people with issues. But are there anything sort of in the quote unquote natural sort of area that helps facilitate sleep in any way?
Well, as you might imagine, I'm frankly reluctant, and this for a variety of reasons, to recommend or endorse a specific supplement for sleep. In addition to melatonin, which we've discussed at some length, and it does seem to work for some people, even if it's again a placebo effect. You and your listeners are probably familiar with, for example, valerian, which has been used for centuries as an over-the-counter sleep aid. I've never used it, but it is in fact approved as a sleep aid in some countries, including, I think, Germany.
Yeah.
I don't know much about the potential side effects, but can point to its use for literally hundreds of years around the globe as a sleep aid. But from the standpoint of data-driven recommendations, I think there's pretty credible evidence for supplements with magnesium or magnesium and zinc and helping optimize sleep quality. But beyond that, I'm frankly not a big proponent of taking in particular the prescription medications for sleep, unless it's in the very short term and for a very specific reason, and provided from a physician who actually understands sleep disorders. So
yeah, that's fair. All right, well, maybe we could finish on, if you were to create the perfect preconditions and environment for sleep, what would they be? And this may involve food and food groups such as carbs, fats, and proteins, the amount of water, and the amount of time that one might be best to avoid eating or drinking before sleeping.
Well, okay, so I think going to bed hydrated is a great strategy. We do sort of desiccate a little bit while we're sleeping. Although each individual will need to sort of titrate the amount of water they can intake and still maintain sleep continuity, right? Because if you have too much water, you'll end up in the middle of the night needing to relieve oneself, and that's just kind of sleep disrupting, of course. And the relieving issue is, in fact, another reason to avoid at least in excess alcohol, because alcohol, of course, is a potent diuretic. You just don't want to have a potent diuretic just before bedtime, and for obvious reasons. But as for food, I think avoiding going to bed hungry, but also avoiding going to bed stuffed, is kind of the key. So with the content of the food being more or less secondary, in other words, carb versus fat versus protein, I just don't think there's really great compelling data to say you eat these type of this specific type of food versus another type of food, your sleep is somehow better. I'm just not convinced that's the case. But I have seen some interesting studies, well-performed studies, whatever, that going to bed 2 to 3 hours after the last meal is probably ideal from the standpoint of digestion. In fact, human studies have shown that eating close to bedtime is negatively associated with a variety of sleep quality variables. So, I in terms of hydration, I think a great approach for a lot of people is just a cup of hot herbal tea. There's no caffeine. It's quite hydrating. It's pleasant, and it just might be it just might be a good thing to consider. But when you talk about preconditions, so setting hydration and food aside, this would go back to what I was talking about with good sleep hygiene a moment ago. You really want to be in a dark room, set at an optimal temperature, very quiet, or perhaps white noise. Some people seem to find a white noise generator helps. A mattress with adequate support, and the room itself should be dedicated to sleep, to the extent that's possible. I know it sounds like a very sort of ivory tower recommendation, but it is true that you're in a room that you also spend a lot of time watching TV and doing other stuff. It's just really ideal for achieving good restful sleep, because you in your own way are associating that room with other activities other than sleep, or with activities other than sleep. So those would be my sort of recommendations for setting the stage, or the preconditions, as you say, for a good night's sleep.
That's great, and I think that brings us about to time. So Patrick, thanks so much for taking the time out of your busy schedule to come on the show. I'm glad we figured out a time that worked, and
we did. And thank you for having me. It's been a pleasure. I'm happy to. There's a lot more ground to cover, as you would know. And so, if you ever would like to chat again, I'm happy to do so. And best of luck with everything. And thanks for having me.
Absolutely. Thanks very much. All right.
Take care. Thank you.
Cheers.
Bye-bye.
Bye-bye.